Have you ever stopped to think about why a diamond is one of the hardest things in the world, but a block of ice just shatters? Or how a metal wire can carry electricity, but a glass window stops it dead in its tracks? I mean, they're all solids, right? But they couldn't be more different. Well, we're about to pull back the curtain and look at the secret internal architecture that makes everything the way it is. So let's kick things off with a pretty simple question. Take a look at table salt. You can literally see it forms these perfect little cubes. But then you drop a glass and it shatters into a million random sharp pieces. They're both solids, so what is going on there? What's the fundamental difference? Well, the answer isn't on the surface. It's deep, deep inside, down at the atomic level. And it really all comes down to how their fundamental particles are arranged. For solids, you basically have two choices. You either have perfect repeating order or you have total chaos. And that brings us to the two main families of solids. On one side, you have crystalline solids, like our salt or a diamond. Their particles are locked into this perfect repeating 3D grid that we call long-range order. And because of that order, they have a very sharp, precise melting point. Then on the other side, you have amorphous solids, like glass or plastic. Their particles are just a random jumbled mess. They only have short-range order, which is just a fancy way of saying an atom knows who its immediate neighbors are, but that's about it. And that's why they don't really melt. They just soften gradually over a range of temperatures. You know, here's a fantastic way to picture this. Think of a crystalline solid as a perfectly organized, super disciplined classroom. Every single student is in their assigned seat, row after row, perfectly aligned. Now, an amorphous solid, that's the same classroom, but right after the bell rings. Students are just scattered everywhere, sitting wherever they want. One is predictable and orderly, the other is completely random. Okay, so let's focus on that disciplined classroom for a bit. We're going to zoom way in on crystalline solids and try to understand the actual blueprint that creates their perfectly ordered structure. The master plan for any crystal is something called its crystal lattice. Now try to imagine this as a vast, invisible 3D scaffolding stretching out in all directions. It's important to know this isn't the atoms themselves, it's the grid of points in space where the atoms are supposed to go. This framework is what locks in that perfect repeating order. So if the crystal lattice is an entire skyscraper, then the unit cell is the blueprint for a single floor, which then gets copied and stacked over and over and over again. It's the absolute smallest repeating piece that contains all the information of the entire structure, which is amazing, right? It means if we can just understand this one tiny box, we can understand the whole crystal. So let's do that. Let's look inside this box. We're going to focus on the most common type, which is a cube. And we're going to do something that sounds kind of simple, but is incredibly important. We're going to count how many atoms actually belong to a single unit cell. And this isn't just for fun. This number is the key that lets scientists calculate a material's density from the ground up and predict its most basic properties. Now, in this cubic family, there are three main arrangements you'll see. The simplest one is called, well, simple cubic, or SC. It's just got particles at the 8 corners. Then you have body-centered cubic, or BCC. It has those corner particles, plus one right in the dead center. And finally, there's face-centered cubic, FCC, which has the corner particles plus one in the middle of each of its 6 faces. Okay, so let's count. For a simple cubic cell, you look at it, you see 8 atoms on the corners, and you might think, easy, 8 atoms. But here's the trick. Each of those corner atoms is actually being shared by 8 neighboring cubes. Our little unit cell only owns 1/8 of each of them. So you take 8 corners and multiply by 1/8, and you get a grand total of exactly 1 atom per unit cell. Kind of surprising, right? Right. Now, for body-centered cubic, we start with the same logic. We still have those 8 corners, each giving us 1/8 of an atom, so that's 1 atom right there. But then we add that extra atom that's sitting right in the center of the cube's body. That one isn't shared with anyone else. It belongs completely to this one cell. So that's 1 from the corners, plus the 1 from the center, for a total of 2 atoms. A little more crowded in this box. And finally, face-centered cubic. You know the drill by now. We start with our 1 atom from the corners, but now we have these 6 atoms, 1 on each face of the cube. Each of those face atoms is shared between just 2 cubes, right? So our unit cell gets half of it. 6 faces, each contributing half an atom, that gives us 3 more atoms. Add the 1 from the corners, and we get a total of 4 atoms. This is the most densely packed of the cubic cells, and that's a huge deal for the properties of materials like gold and aluminum. Okay, so we've seen the blueprint, the arrangement, but a crystal's properties don't just come from the layout, they depend on what the building blocks are.
What are the particles and what's the glue holding them all together? This gives us what you can think of as four main crystal personalities.
First up are ionic solids, and our friend table salt is the perfect example. Here, the building blocks are positive and negative ions, and they're held together by a really powerful electrostatic attraction. Seriously, think of it as super strong static cling. This makes them hard and gives them a high melting point, but it also makes them brittle. If you hit them and shift the layers just a little bit, suddenly positive ions are next to positive ions, and they repel each other, shattering the crystal. Next, we have covalent network solids. Now, these are a whole different beast. In materials like diamond or quartz, individual atoms are joined to all their neighbors by super strong covalent bonds. They're all sharing electrons. This isn't just a grid of attractions. The entire crystal is basically a single gigantic molecule. And that is why diamond is one of the hardest substances we know of and has an absolutely insane melting point. Personality number 3, metallic solids. The mental image here is key. Picture an orderly grid of positive metal ions just sitting in this free-flowing sea of shared electrons. These electrons don't belong to any single atom. They can just zip around the entire structure. And that free-flowing electron sea, that is exactly why metals are such fantastic conductors of both heat and electricity. And finally, we have molecular solids, like a chunk of ice or dry ice. In these, entire molecules, like a whole H2O molecule, sit at the lattice points. The forces holding these molecules together are much, much weaker than anything we've looked at so far. And because that glue is so weak, these solids are usually soft, they have low melting points, and they're not very good at conducting electricity. So let's just pull that all together for a second. It's a pretty clear story, right? Everything we see on the outside, whether something is hard or brittle or conducts electricity or melts easily, is a direct result of what's happening on the inside. Ionic solids are hard and brittle because of that strong ion attraction. Covalent networks are crazy hard thanks to their web of shared electrons. Metals conduct because of that electron sea, and molecular solids are soft because their glue is weak. The particle and the bond define the property. Simple as that. Now, we've spent all this time talking about these perfect, disciplined, repeating structures. But here's the thing. Reality is always a little messier. And it turns out there's a real beauty in the flaws. Because in the real world, perfect crystals don't actually exist. And that leads us to a really crucial question. After all this discussion of perfect lattices and unit cells copied a billion times, are the crystals we find in nature or the ones we make in a lab ever truly perfect? Does that perfectly disciplined classroom actually exist anywhere? The answer is a big, resounding no, not even close. Every single real-world crystal has what are called defects. They're tiny errors, little irregularities that disrupt that perfect repeating pattern. It's just a fundamental fact of nature that achieving absolute perfection is impossible. And these tiny mistakes come in a few common flavors. You can have a vacancy defect, which is literally just an empty spot where an atom should be. You can have an interstitial defect, where an extra atom gets jammed into a space where it doesn't belong. Or you can have an impurity defect, which is when a totally different element sneaks in and takes the place of one of the host atoms. But, and this is the most important takeaway of this entire explainer, these flaws are not failures. They are absolutely essential. The brilliant colors in gemstones, that's because of impurities. The incredible power of the semiconductors in your phone, that's all about carefully controlled defects. The strength of steel alloys, you guessed it, it's the flaws. It turns out a perfect crystal would actually be far less interesting and useful. So we're left with this final thought. A single missing atom, a tiny, invisible flaw, can completely change the character and properties of a material, making it stronger or more colorful or more useful. If that's true for a solid crystal, what does that say about the power of small imperfections in other complex systems? Something to think about. Thanks for tuning in.